Hello, welcome to IEEE Conference on Energy Conversion 2021. My name is Razman Ayob. I will present the photovoltaic emulator using the particle swarm optimization. Okay, the presentation will consist of 4 parts. The first part is the introduction. The next part is the methodology. The third part is the results and discussion. And the last part is the conclusion. We start with the introduction that covers what is PVE, the control strategy, and the resistance comparison method or RCM, and the last one is the objective and scope. Okay, what is photovoltaic emulator or PVE? So PVE is a specialized power supply used in the development and testing phase of the PV generation system. Okay, PVE operation change with the load similar to an actual PV module. Okay, ambient condition that covers the irradiance and temperature also affect the operation point of the PVE. And lastly, an algorithm called the control strategy is needed to determine the operating point quickly, accurately, and consistently. Okay, we move on to the next part, which is the control strategy. So basically, this is a literature review. The commonly used is the direct referencing method or DRM. It is easily to implement but has oscillation problem. The hybrid DRM improve this problem by reducing the oscillation problem, but the hybrid DRM is complex to be implemented. Next is the resistant feedback method, which has no oscillation problem, but the problem with this is the require specialized PV model. Okay, and lastly, the resistance comparison method or RCM. It also has no oscillation, but the problem it has a high computational burden. Okay, so we move on to the resistance comparison method or RCM. You can see here as the method goes to the left, it is much more lower computation burden. This is important because higher computation burden will limit the speed of the transient response of the system, as well as it is much more costly. So the original one is the resistance comparison method using the perturb and observe with a fixed step size. Next, the next less computation burden is the integral controller. And we need the faster computation burden, and we can see that particle swarm optimization is has a very low computational burden. So the proposal is to use a PSO in the resistance comparison method. So objective and scope. So the objective of the study is to simulate the PVE using RCM resistance comparison method computed with a PSO, which is called the RCM-PSO. And this method is benchmarked with DRM since it is the common PVE available. Okay, and then the scope of the study is to simulate this with a single diode model with no partition shading, the buck converter with continuous current mode operation, and lastly the PI controller. Okay, and also the simulation is done using MATLAB, Simulink, and only the resistive load is tested. Okay, we move on to the second part of the presentation, which is methodology. Okay, this covers the design of the PV model, okay, buck converter, PI controller, the control strategy, and the proper resistance comparison method, particle swarm optimization. Okay, the first one is the photovoltaic model. You can see here this is the standard single diode model, and the equation is shown below. Okay, the IPV equals to IPH and so on. Next is the buck converter. You can see here this is the equivalent circuit of the buck converter. To design this, you need to calculate the L and C. Okay, for the continuous current mode, you have to calculate the L correctly. This is the formula to calculate the L. And also the output voltage ripple factor, which in this case we choose 2% maximum. You can calculate using the C. Okay, this equation. Okay, next is the PI controller. You can see here, this is the block diagram for the designing the PI controller. Okay, you can see here, this is the transfer function used to design the PI controller, which is must have, and also this is the PI controller itself, the transfer function of the PI controller. Okay, next is the control strategy. Okay, as I mentioned in the objective, we use the DRM as a benchmark. So this is the transfer function for the block diagram for the transfer function, or the control strategy for the transfer function. Okay, you can see here we have already discussed the PV model, the PI controller, and the buck converter. PWM also falls into the buck converter. So basically, control strategy is just way how you connect each component. Okay, this is the conventional one. This is the proposed RCM-PSO. So there is a bit different at the left side. You can see that there are PSO before the PV model, and also instead of using only V out, we use both V out and I out to the feedback. Okay, this is the proposed RCM-PSO. You can see here, this is the general equation used in the PSO. There are only two, the velocity and the position. Okay, the first flowchart is this one. This one is basically just to start to determine whether there are changes or first time run. If no, it will end and restart again the algorithm. If yes, it will load the characteristic of the PSO, okay, the parameters of the PSO, and then you run the PSO itself. So basically, you have to determine the fitness function, which is comparing the RPV with the Rout. Okay, RPV is from the PV model and Rout is from the sensor. Okay, and then determine the best position for the particle and best position for the global. Okay, and then you have to update the velocity and then run it again. We move on to the third part of the slide, okay, which is result and discussion. Discover the oscillation, the accuracy, and the transient response. The first one is the oscillation. Okay, you can see here, this is the output voltage ripple factor with different Rout for the PVE using RCM-PSO and DRM at 1000 watt per meter square and 25 degrees Celsius. As I mentioned before, the ripple factor should only be less than 2%. But if you can see here, the DRM is more than that when the output resistance is high. Okay, so you can see here the proposed RCM-PSO has a lower ripple factor at high Rout compared to the conventional DRM. Okay, the proposed this means that the proposed method is much more stable when compared to the conventional method. And the instability of the DRM is caused by the transient characteristic used to determine the operating point. Okay, but the proposed method doesn't use this one. Okay, so since the proposed method doesn't use the transient characteristic, it is much more stable because it is calculated using PSO. Next is the accuracy. You can see here there are two results. One is plot on the IV characteristic curve. One is the error. Okay, so you can see here this is the comparison. Okay, and you can see that the proposed RCM-PSO has lower E error at high output. Okay, high output resistance compared to the conventional DRM. Okay, this shows that this accuracy is caused by the stability. Okay, the proposed RCM-PSO is much more accurate compared to the DRM. Okay, this low accuracy of DRM is due to the oscillation problem as mentioned before. The last result is the transient response. You can see here there are two transient response, which is at 1 ohm and 40 ohm. You can see that at 1 ohm the response is the same for DRM and RCM-PSO. However, at higher output resistance, which is 40 ohm, okay, the proposed RCM-PSO response slower when compared to the DRM. Okay, this is due to the limitation of the PI controller. So if you replace the PI controller, the response can be faster. Okay, we can conclude it. Okay, so the conclusion is the proposed RCM-PSO has better stability and accuracy when compared to the conventional DRM. Okay, and the RCM-PSO able to maintain low oscillation, which means that better stability. And also, however, the RCM-PSO has a slow transient response during high load. This limitation is caused by the slow response of the PI controller when the load is high. Okay, so this problem can be overcome by replacing a faster controller. Okay, this is the end of the slide. Okay, if you have any further question, you can ask during the conference, or you can visit this website to ask the question. So thank you. Okay.